So I'd like to now discuss two big questions that were answered by making use of the redshifts to study the universe. And the first question may sound a little strange to someone who grows up in science in the current epoch. But that question is the scale of the universe bigger than our own galaxy? This was the topic of a famous debate between two opponents, Curtis and Shapley, in 1920. And the idea is the following. Astronomers had been looking at stars throughout our galaxy, using the best means possible to determine the distance to the individual stars. But there was always a great deal of uncertainty in those distance measurements. There were objects that were seen that looked fuzzy. They did not look like stars. And in fact, we would call them galaxies today. But it wasn't clear whether these were small objects within the Milky Way or, in fact, other galaxies like the Milky Way, but outside the Milky Way. In particular, objects like Andromeda, our nearest neighbor. So this debate between Curtis and Shapley was trying to come to grips with the physical understanding of the location of the objects and the size of our universe. So there were arguments that both made, both proponents, and essentially one of Shapley's arguments, and Shapley took the side that the Milky Way actually comprised the whole stellar universe. Everything that appeared to emit light was part of the Milky Way. So one of his arguments was, well, if you look at the angular size, of these purported galaxies, and you said they were actually as big as our own galaxy, they must be very, very far distant because the angular size was so small. And based on all the measurements that people had gathered on stars and other things within our galaxy, these were hundreds of times further away than anything that people had seen. So people were not in the mood to contemplate that they could have been wrong by such an enormous factor. But it wasn't just, we can't imagine it. There were actually observations that purported to show that the objects that we call galaxies were actually rotating. So I'd like you to look at this beautiful galaxy. It's called the Pinwheel Galaxy for good reason. It looks stunning. And observers at the time actually claimed they could see this turning. By taking successive exposures, they were actually able to detect motion of this galaxy. Well, if it was as far away as some people claimed, in other words, outside our own galaxy, it would be easy to calculate a lower limit to how fast it was moving. And the arms would be moving faster than the speed of light. So relativity would have argued that this was impossible, and therefore the galaxy couldn't possibly be so far away. Now, as it turned out, this observation proved to be an error. Curtis, on the other hand, argued that Andromeda and objects like it were separate galaxies, so-called island universes. That's a term that comes from philosophers, Kant, who talked about hypothetical models for the universe. And Curtis's argument was really based on morphology. He identified features in the small objects, like dust lanes, that he thought resembled features in our own galaxy. He also looked at a a particular class of stars called nova, which appeared to exist in great numbers in these small objects. And the only explanation he could come up with, if they were the same nova that he was familiar with, was this was a much bigger collection of stars than would be possible if it were within our own galaxy. So there was one final piece of evidence that he was influenced by, and that was that these galaxies, or these objects over which he was quarreling, appeared to have large Doppler shifts, meaning they appeared to have large velocities. Now, he did not really follow this reasoning to its logical conclusion, but it was sufficient for him to say they're probably outside our own galaxy, because nothing else we see in our galaxy has that sort of velocity. In fact, people had been studying these objects using the Doppler methods even before this debate took place. And so in the early 1900s, Slipher had actually measured the velocities to these so-called spiral nebula. And what he found was that the preponderance, 12 of 15, appeared to have blue shifts. Appeared to have red shifts as opposed to blue shifts. They appeared to be receding from us. So this would be very strange if these were all objects that were distributed within our galaxy, because if you look at stars, on average, half are approaching us and half are moving away from us. Why would these spiral nebula be different? But on the other hand, it would also be strange if they were outside our galaxy. Why would they be running away from us? So neither Shapley nor Curtis really followed the trail, the scent that was laid down by the Doppler shift information. But it wasn't too long before the debate was actually settled. So Edwin Hubble used the 100-inch telescope at Mount Wilson to measure distances to objects that were the subject of this particular debate. Hubble used a method that astronomers today call the standard candle method. And the idea is very simple. If you know the luminosity of a source of light and you measure its flux, then you can infer its distance, because the light spreads out on a sphere of radius r over an area of 4 pi r squared, and that allows you to relate the flux and luminosity. But you have to know the luminosity, and you have to measure the flux to actually infer the distance. What he did was a little bit more involved. His standard candle was a variable star called a Cepheid. Not all stars burn with constant luminosity, and this is a very special, peculiar star that happens to change its brightness over time. In fact, it's a very human scale of time, over a period of weeks to months. So that's interesting, but there's one other essential item about the Cepheids that make them useful to Hubble. It's that the period of the variation of the star is directly related to the luminosity of the star. Now, this is something that no one would have predicted, but it's been empirically observed. A star in the nearby neighborhood, we can measure the period over which the light varies, and we can calibrate its brightness. We can relate one to the other, and this is called the period-luminosity relationship. Okay, so what do? We go, or I should say, what does Hubble do? He goes and he looks for Cepheids in other galaxies, and he watches them vary in brightness. Then he knows from the local calibration how bright those stars are at any given time, and he measures the flux, and from that he infers the distance. So Hubble did this, and he published his results in the mid-1920s, And what he found was that these objects were far beyond the edge of our own galaxy. So he settled the debate, but also in one fell swoop, he made the size of the universe much, much bigger than it had hitherto been. So although people had suspected maybe that Curtis was right, there was a lot of drama to this. And you should think back to your favorite movie where the protagonists are making their way through the jungle and everything is blocked, their view is blocked. And suddenly they emerge on a precipice that's 2,000 feet above a valley. That's the sort of change in perspective that astronomers had as a result of learning that these objects, these spiral nebulae, were actually galaxies outside our own. The universe got a lot bigger in one fell swoop. But the story actually continues beyond this. So by 1929, Hubble had taken the distances he measured using the variable stars, and he plotted them against the velocities Slipher and others had measured using the Doppler relation. And what he discovered was there appeared to be a linear relationship between distance and velocity. And today, this is called Hubble's law, and the constant is called Hubble's constant. And this has become tremendously important in astronomy. So just to write it out, the velocity is equal to the Hubble constant times the distance to the object. So Hubble knew the velocity from the Doppler spectral line measurements. He knew the distance from the standard candle measurements, and he determined that more distant objects were moving away from us more quickly. So not only was the universe bigger, but it was expanding, and it just became a lot more interesting. So there are a few historical notes that I have to mention. One is that the actual value that Hubble got for the Hubble constant was way off. I mean, roughly a factor of 10. And that involves complications in the standard candles he used. And another interesting note is that a theorist, Georges Lemaître, had already inferred the existence of this linear relationship 2 years before Hubble did. He used Hubble's own data. So there's a lot of, history that needs to be fully explored. But from a practical astrophysical point of view, this linear relation has been studied and confirmed and continues to be thought to be correct and is still called Hubble's law even today.